What's up, everyone? Let's talk about multivariate analysis of variance, or MANOVA. So when do you use MANOVA? Well, you use MANOVA when your dissertation committee throws another dependent variable at you. So it is designed for cases where you have one or more nominal between subjects IV with two or more categories, hence they are variables. And you have two or more DVs, so that would be the same participant scored on each DV, and they need to be measured on a ratio or interval scale. So like I said, you walk in to your dissertation committee with a simple ANOVA, and then next thing you know, they're like, well, you also should look at this other DV. And so that's why I teach you this, because this is going to help you if they throw another dependent variable in your dissertation. So note that the dependent variables that you analyze, because there's more than one, should be related theoretically and actually in terms of correlation as well, so statistically. So let me give you an example of this. So why do people vote? Is it a sense of civic obligation or patriotism? So let's say the hypothesis of this is that people vote primarily due to their sense of civic obligation rather than due to their level of patriotism. So they vote because it's civic duty, not so much because of patriotism. So we've got an independent variable, that is your voting status in the last election. Here we've coded as 1 did not vote, 2 is voted. Then we measured these folks on sense of civic obligation. It's a 0 to 200 score. Higher is more sense of civic obligation, and that is our primary DV according to this hypothesis. Why? Because we're saying it's that one, not the other one, that primarily drives their voting behavior. Here's the other one. Their second DV is level of patriotism. Again, 0 to 200, higher is more patriotism. So in this study, let's say they get 60 eligible adults and they're asked if they voted in the last election, and they complete a questionnaire that measures both their sense of civic obligation and their level of patriotism. This would be a quasi-experiment. We're not randomly assigning people to vote or not. And there's your means. You can see, just sort of looking at the bar charts, it looks like those who voted are higher on the left, so they're higher in sense of civic obligation, and directionally higher in patriotism as well. So here's a scatter plot of sense of civic obligation and level of patriotism, and also the correlation coefficient. And you can see these two dependent variables are actually, decently correlated, moderately correlated for sure, at 0.53 R, which if you square it, you get R squared. So you have about 28% of the variability, and one variable can be accounted for by the other. So they have 28% overlap is how I would think about that. So they're definitely correlated variables, even though they're both higher in those who voted. So why don't we just do some separate independent samples t-tests between those who voted and didn't vote? We can compare voters, non-voters on civic obligation. Then we can do a second one where we compare them on patriotism. Having been in this class, you probably know there's a reason. It's a bad statistical choice for the following reasons. Number one is the usual culprits, type 1 error rate inflation. So the MANOVA starts with an omnibus test of all the DVs at one time. So that guards against type 1 error inflation, meaning the MANOVA has a special effect in it called the multivariate effect, and it will be significant if there's an effect of the independent variable on either DV. So in that sense, it is an omnibus test, and it keeps you from doing two tests. You can just do one. So the multiple ANOVAs would have inflated the type 1 error, but with the ANOVA, it's just one test. So reason number two, you might be interested in the multivariate effects themselves. That is, MANOVA puts together the two dependent variables and analyzes them at one time in what's called a centroid or a vector. So it says, in the case of this example, do those who vote and don't vote significantly differ on combined patriotism / sense of civic obligation? And so that is something unique to this particular test. So you could, for example, find that if you analyze them individually, you don't really find a difference, but taken together, it's more than just the sum of their parts. You do find significant difference between those who voted or not. You would lose that if you did separate t-tests or MANOVAs. And then finally, you want to account for the intercorrelation of the DVs. So these two variables we know overlap fairly substantially, and that's variability that can be accounted for by, or that's differences between those who vote and don't vote that can be accounted for by civic obligation or patriotism. So the MANOVA assigns it to one of the variables and then not the other, so that you're getting independent effects across the dependent variables. That might be important to you. So it excludes redundant information from the analysis. So what's the solution here? Yes, you should use MANOVA when you have two dependent variables. It simultaneously evaluates the effect of IVs, and you can have more than one in MANOVA, on both DVs combined at the same time. So assumptions, some of these are the usual, one is definitely not. Independence of observations, you've got different people in the different cells of the design. Here's one that I think's new to you guys, multivariate normality. So this, you've had normality in the past, which said that the scores in each level of the dependent variable are approximately normal. But this is more than that. It's not only in the univariate sense, but also in the multivariate sense. It says that all dependent variables are univariately normally distributed within each cell of the design. That's what you're used to. But also that all combinations of DVs, that is multivariate normality, all combinations of DV are also normally distributed. So the above has to be true for each level of the IV, or if there's more than one IV, for all cells in the design. So everything's normal, basically, is the way to think of this, and all pairs of things are normal. So MANOVA, like all of the ANOVA family, is robust to moderate deviations from this. So if it's a little bit violated, not a big deal, particularly if the sample sizes are equal. So I don't think you've seen this one, the homogeneity of covariance matrices assumption. The homogeneity of covariance matrices assumption has two parts to it. One is the usual homogeneity of variance, and the second is the homogeneity of covariance matrices. So here we go. Part one of this assumption is that the variances of the DVs are similar across levels of the IVs. That is your homogeneity variance assumption. I usually say the spread of scores is approximately the same across the different levels of the IV or cells of the design. The newish part is that the covariances also have to be similar across the levels of the independent variable. So that is what we call the homogeneity of covariances. So together, these two are the homogeneity of covariance matrices, because they're actually all part of one matrix in matrix algebra. For those who really want to nerd out, that's an example shown in the upper right hand of the screen. So one way of thinking about this, for those who aren't math geeks like myself, is that the correlation between the DVs is similar across the IV level. So the dependent variables are approximately the same direction and magnitude of correlation for each level of the independent variable or cell of the design. So, for example, this would state that the correlation between civic obligation and patriotism in the example is similar in direction and magnitude for voters and for non-voters. Whatever that correlation is, it's about the same for voters and non-voters. This is tested in SPSS using Box's M test. That Box's M is a test of the homogeneity of covariance matrices assumption for MANOVA. And here's your rules. If Box's M sig is greater than 0.05, then the homogeneity of covariances matrices is met. The assumption is good to go. If Box's M sig is less than 0.05, then you have violated this assumption. So do you give up? Well, here's the impact. If the group sizes are relatively equal in the levels of the independent variable, then what likely will happen is a slight reduction in power. If you've got markedly unequal sample sizes, your type 1 error rate will be inflated. Surprise, surprise. And so what I usually recommend you do is if you violate boxes M, it means you haven't met all the assumptions of MANOVA, you can just use Pillai's trace, which is one of the multivariate stat choices. There's 4 of them total, instead of the usual Wilks lambda. So use Pillai's choice if you violate the homogeneity covariance matrices assumption. So there are multiple steps in conducting MANOVA. The first step is to conduct what we call the multivariate test, and that is a test of group differences on the combined DVs. So the dependent variable in MANOVA is a linear combination of all dependent variables, something that we call a centroid or a vector. It puts the DVs together into a single thing in 3D space, and tells you test whether the groups differ on this combined dependent variable. So combined patriotism / sense-specific obligation, for example. By combining the dependent variables into a single multivariate dependent variable, it removes the redundancies or overlap or correlation between the dependent variables. It's only counted one time. The combined analysis of multiple dependent variables is what makes MANOVA special, that you can do a single test to compare multiple dependent variables to see if there's an effect of an independent variable at one time is what makes it special. So in this step, you determine if there's a significant effect of the independent variable on the multivariate centroid, that is the DVs combined. You determine if the groups significantly differ on the combined DV. You interpret this by using what are called multivariate tests, something totally new, that come in a table in SPSS, and you have 4 choices of which multivariate tests to interpret for determining if indeed the groups differ on this combined dependent variable. The first one is Wilks lambda. Wilks lambda is the most common multivariate test. Use it when in particular, your box's sig is greater than 0.05, so you've met the covariance matrices assumption. And you've got equal sample sizes. The second choice you have is Pillai's trace. This one is more robust to deviations from the homogeneity covariance matrices assumption. So as I stated earlier, this is the one you use when you've got significant box M indicating that you have violated the homogeneity of covariance matrices assumption. You can also, it's better to use when you've got unequal ends or you've got highly correlated dependent variables. Third one is Hotelling's trace. Hotelling's trace is basically the 2-level IV version of Wilks lambda. So when you've just got one independent variable and it's got 2 levels, box's sig is not significant, meaning you've met the homogeneity of covariance matrices assumption. You can use Hotelling's trace instead of Wilks lambda. And finally, Roy's largest root. Never used this one myself. This is the one that apparently you use when one of the dependent variables is particularly dominant among the others. So to interpret whichever test it is you end up choosing, you look at the multivariate sig for that test. If it's less than 0.05, then you conclude there is a significant effect of the independent variable on the combined dependent variable. That is, the IV levels differ on at least one of the dependent variables. You would then need to conduct step-down analysis to determine for which dependent variables the IV groups differ. So step-down analysis we'll talk about in a sec. If your multivariate sig, on the other hand, is greater than 0.05, then you know from this one test that the groups formed by the independent variable do not differ on either of the dependent variables. That is, there is no effect of the independent variable on any of the dependent variables. And you're done. So you conclude there's no difference between the groups on any of the dependent variables, and with one test. So the summary table presented on this page just sort of tries to give you a feel for when you would use each of the 4 different multivariate tests. I talked about most of this already. Wilks lambda is the most common, but the assumptions need to be met. Pillai's trace is more robust. You can use it when you violate the homogeneity of covariances assumption. Hotelling's trace is when you're essentially doing a t-test version of MANOVA, and then Roy's largest root. What it says there. I've never used this one in my life. So the next step in conducting MANOVA is, when it's significant, is to actually do what's called step-down analysis of the multivariate effect. And what this does is it tests the relative importance of the DVs for the multivariate effect of the independent variable, meaning you see which DVs it differs on and you order them. So as part of this, you have to identify which dependent variable you think is the most important or primary, and that should be based on the hypothesis or on theory. And then you order the remaining dependent variables from most to least important subsequent to the primary. So you have primary, secondary. If you got 3 DVs, you'd have a third one as well. So there are multiple steps to follow, which I'll explain. Number 1, first do a step-down ANOVA of the primary dependent variable. So this is actually printed on the SPSS output as part of the MANOVA. So it's a piece of cake to do this one, but primary dependent variable, let's see if the groups differ on my primary dependent variable based on the ANOVA that comes as part of the MANOVA output. For this, you want to use a Bonferroni corrected alpha level to interpret the statistical significance. And you'll recall Bonferroni corrected alpha level is the alpha you want to keep, so 0.05 usually divided by the number of dependent variables that are involved in your MANOVA. So that's a little different. It's instead of like number of tests, it's number of dependent variables. So if you had 2 dependent variables and you wanted to maintain an alpha of 0.05, your Bonferroni corrected alpha level would be 0.05 divided by 2, or 0.025. And this tests if the independent variable groups differ on that primary dependent variable of interest. So it's essentially just a one-way ANOVA or one-way t-test, depending on how many groups you got. The next step of step-down analysis is to run an ANCOVA on the secondary dependent variable, where you use the primary dependent variable as a covariate. So do the groups differ on the secondary DV after removing differences associated with the primary DV? Use that same alpha Bonferroni corrected to determine the statistical significance of the IV effect in the ANCOVA. You use just regular old 0.05 for the covariate, which is the primary dependent variable. And what this tests is if the IV groups differ on that secondary dependent variable after accounting for differences on the primary dependent variable. So it is we're stepping down through the analysis. If you had 3 DVs, you would continue with the step-down analysis. You would run another ANCOVA, and in this one, the dependent variable would be that third dependent variable, so the third most important one. And the covariates would be both the first and second DVs. So it would be an ANCOVA of the independent variable's effects on that third dependent variable adjusted for the first 2 dependent variables. Again, alpha Bonferroni to interpret the significance of the IV. So you would repeat this step 3 of doing an ANCOVA adjusting for all prior DVs until you run out of DVs. That's basically step-down analysis. So at each step you're saying, okay, does this dependent variable, most important one, differ? Second test is, does the second most important one differ after you take the first dependent variable into account? So forth down the line, you step down. Decision rules. For the multivariate tests, if multivariate sig is less than 0.05, reject the null. That tells you that the groups differ on the combined dependent variable. If multivariate sig is greater than 0.05, the groups do not differ on the combined dependent variable. For the step-down ANOVA and ANCOVAs, if sig is less than the alpha Bonferroni, you reject the null, which tells you the groups do differ on this DV. If it's greater than 0.05, the groups do not differ on this particular DV. There's your Bonferroni formula again. And there's an example again. So for the covariates that are used in the step down in ANCOVAs, you just use 0.05. And so if the sig for the covariate is less than 0.05, you know that the covariate significantly adjusted the dependent variable, or covariates. If the covariate sig is greater than 0.05, you retain the null, meaning the covariate did not significantly adjust the dependent variable. Measures of effect size. So for the multivariate tests, I didn't actually know these existed until fairly recently. But for Wilks lambda, you can convert Wilks lambda into partial eta squared, which is sort of like eta squared. It tells you the proportion of variability accounted for that is as yet unaccounted for in the model. And that's the formula for doing so. Poli's trace, if you use it, is itself a measure of effect size. The Poli's trace, V itself, tells you the proportion of variance explained by the independent variable. And so in that sense, kind of like R squared. For the step downs, ANOVA and ANCOVAs, you also can calculate partial eta squared. And SPSS actually does calculate this, I think, correctly in the SPSS output. It's the sum of squares for the IV divided by the sum of squares of the IV plus the error. So it's what proportion of variability in the dependent variable that is as yet unaccounted for can be explained by the independent variable's effects. So APA format for your multivariate tests, you would this is the sort of standard way of doing your multivariate effect. It's either Wilks lambda applies Hotelling's or Roy's. You put what that number is there to 2 decimal points. No one knows really how to interpret those things, so SPSS also gives you an F equivalent of it. So you end up putting both the multivariate stat itself plus the F equivalent of it. And all that comes straight from your SPSS output. For the step down ANOVA and ANCOVAs, it's the usual, except you've got alpha Bonferroni instead of just alpha out there. So that's your F value to 2 decimals, P less than or greater than alpha Bonferroni, and then your eta squared, which is actually partial eta squared. And again, all that comes straight from your output because SPSS does the eta squares correctly. So let's go through an example. Let's do the one that we talked about earlier. Why do people vote? Is it civic obligation or patriotism that is most associated with voters and non-voters? So the hypothesis, again, is that people vote primarily due to their sense of civic obligation rather than due to level of patriotism. In this analysis, our independent variable is voting status in the last election, which we've coded here as 1 did not vote, 2 voted. We gave them that questionnaire where we got a civic obligation score. Higher scores indicate more sense of civic obligation a person has. And that, again, according to the hypothesis, is our primary dependent variable because people vote primarily due to their sense of civic obligation. That's the one we're banking on. Second dependent variable was also a questionnaire of patriotism, where again higher values from 0 to 200 indicate having more patriotism, and this is our secondary DV. So there's the data setup. You got one column for your independent variable, and then one column each for each dependent variable. There's our means, just to show you from the descriptors table of MANOVA what the means are. So these means do get used in your APA write-up. These are the non-covariate adjusted ones, excuse me, for table 1, and they're part of figure 1 as well. So as a first step, it's a good idea to do preliminary correlations of your study variables. So that's what I've done here. There's a correlation matrix of the independent variable and both dependent variables. What we really want to answer here is, are are the DVs correlated? I mean, that's one of the assumptions for MANOVA, that there is some relationship between the dependent variables. There is overlap we want to account for. We will also include the independent variable, where again, higher values on voting status indicate voters. Because it can only be a 1 or a 2. Higher value means a 2, means they voted. So find the correlation for voting status and sense of civic obligation. There it is. It's 0.69. It's got stars, sig less than 0.05. So there's a significant positive correlation between voting status. So as voting status goes up, that is, people who voted tended to be higher on the other variable, sense of civic obligation, which is a fancy way of saying those who voted tended to have a higher sense of civic obligation. Then voting status and patriotism. There it is. So again, we've got a significant correlation. It's positive 0.49. And that tells us as one variable goes up, the other one tends to go up. So again, going up on voting status is being a voter. The voters tended to have a higher sense of patriotism. Finally, the DVs, why we actually did this. Is there a significant correlation between our dependent variables, that is, sense of civic obligation and patriotism? Indeed, there is. 0.529 is positive, and it's statistically significant. It's got those stars, so that tells us having a high, those who had a higher sense of civic obligation also tended to have a higher sense of patriotism. So far, we know that those who vote appear to have both a higher sense of civic obligation and a higher level of patriotism. And that our dependent variables do have some substantial overlap. So if you take that correlation coefficient, square it, you get 0.28, turn into 1%, you get 28% overlap between level of patriotism and sense of civic obligation. So let's do our multivariate analysis of the combined DVs. That is the test of whether those who voted or not differed on combined patriotism / sense of civic obligation. We're going to start with our boxes M test so we can figure out which multivariate statistic we should use to interpret the multivariate analysis. There's boxes M. It's kind of long. You guys are used to Levine's, which is a wide table, but it's kind of long down. Question here is the homogeneity assumption met? That is the homogeneity of covariance matrices assumption. We look at the sig for boxes M test, and if boxes sig is greater than 0.05, we have met the assumption. We therefore would choose Wilks or Hotellings, for example. If boxes sig is less than 0.05, we have violated the homogeneity of covariance matrices assumption, and we would want to use Pillai's trace in that case. So we have not met the assumption. Sig here is 0.002 is less than 0.05, so we violated the assumption. So what's that tell us? Well, it tells us that either the variances weren't homogeneous or the covariances weren't homogeneous across the levels of the independent variable. Just to give you a feel for what that looks like, I investigated a little bit. It turns out the correlation of the dependent variables is pretty different for those who voted and those who didn't vote. Here's two scatter plots. On the left, it's those who voted. You can see you've got something positive correlation between patriotism and civic obligation. On the right, you've got, I mean, not much, but if anything, a negative correlation between sense of civic obligation and patriotism among those who did not, those who did vote. I had it backwards. On the left is those who did not vote. On the right is those who did vote. So those do not appear to be the same relationship, and that is probably why we violated the homogeneity of covariance matrices assumption. So do we give up and go home? No. We just need to use Pillai's trace instead of Wilks lambda or Hotellings t to interpret our multivariate test. So that's what we're going to do. We're going to use Pillai's trace. So finally, our multivariate effects, where we're going to use Pillai's. Is there a significant multivariate effect of voter status? There's our table, lots of stuff in there. We want to go to the bottom. We want to find that Poli's trace line because we violated the assumption. There it is. It's actually not too complicated. Just go ahead and look at the sig. You can see sig is indeed less than 0.05. So the setup question is, can we reject the null that voter groups are similar on combined civic obligation and patriotism? There's our rule. If the sig is less than 0.05, we'll reject that null. If it's greater than 0.05, we'll retain it. As I already said, it's clearly less than 0.05. So what's that tell us? Well, it tells us that the voters and non-voters differ significantly on their combined civic obligation and patriotism. So we don't know which one, could be both or just one of them, but that's why we're going to do that step-down analysis next. There's our APA format, Poli's trace is 0.50. That comes from that value column where it says 0.499. And that is equivalent of an F with 2 and 57 degrees of freedom. That's equal to 28.37, and P is less than 0.05. So because MANOVA is significant, we know that the IV groups differ on at least one of these dependent variables. So we are going to do step down where we order our most important and that second most important DV and do a MANOVA and ANCOVA subsequent. So next step is to do that step down ANOVA of our primary dependent variable. And again, that is a sense of civic obligation because of the study hypothesis that is what drives voters. So the question here is, does sense of civic obligation differ between voters and non-voters? Well, here is the test of between subjects effects table that is actually printed as part of the MANOVA output. We want to look at the line that is for the dependent variable of interest. So this is voting status last election. That's the independent variable. And note that there's a row for sense of civic obligation and patriotism. We want to look at the row for our primary DV, which is sense of civic obligation. We can use a Bonferroni corrected alpha level, so we got to things to be statistically significant have to be less than 0.025. So can we reject the null that voter groups are similar on sense of civic obligation? There's our rule. Sig's less than 0.025 we'll reject. If it's greater than 0.025 we'll retain. And I love it when it's this easy. It's clearly less than 0.025. So we will reject that null. So what's that mean? Well, the voters and the non-voters differ on sense of civic obligation. Specifically, looking at the means that come from the descriptives table, you'll see that voters with a mean of 134.33 had a greater sense of civic obligation than non-voters with a mean of 110.40. We also need to calculate our partial eta squared. So turns out SPSS is calculating these correctly, but there's the formula if you want to do it. Sum of squares for the IV in the numerator divided by the sum of squares of the IV plus sum of squares for error in the denominator. And you get 0.48 if you do the math. And note, under partial eta squared in the table, you get 0.477, which rounds to 0.48. There's our APA format for this, typically goes in the text, so it all comes straight from the table. We have an F with 1 in 58 degrees of freedom. It's equal to 52.91. Our P was less than our Bonferroni corrected alpha level of 0.025, and our partial eta squared was 0.48. So the question now is, do the voter groups also differ on patriotism if we take this particular effect into account? So where these two dependent variables overlap, we give it to sense of civic obligation and say, with what remains, is there a significant difference between voters and non-voters on patriotism? So let's do that. So here is the next step, which is to do an ANCOVA of the secondary dependent variable, that is patriotism. So the question we're asking is, does patriotism differ between voters and non-voters, adjusted for differences in the primary DV, that is their sense of civic obligation? Is there a remaining difference in patriotism? So we're going to run an ANCOVA of voter status as the IB, the secondary DV, patriotism, as the dependent variable, and then we're going to use the primary DV, civic obligation, as a covariate. Going to use Bonferroni corrected alpha level, 0.025. Just showing you where things go. Oh, by the way, for the covariate, we still use 0.05. So our dependent variable is patriotism. So that's up there in the dependent variable box. IV is voting group. CV is our covariate is our sense of civic obligation. And in here we went into the univariate ANOVA. So make sure when you're in here you click the EM means box because you need those estimated marginal means or covariate adjusted means for table 1 and figure 1. So the question at hand, does patriotism differ between voters and non-voters adjusted for differences in their primary DV, which is their sense of a civic obligation? Here's the actual test of between subjects effects. Going to go to that row in there first. That's for sense of civic obligation. This is our covariate, right? So this the sig here tells us whether the covariate significantly adjusted the patriotism means, and we use alpha 0.05. And indeed, sig is less than 0.05. That tells us that sense of civic obligation did indeed adjust the covariate. Did indeed adjust the patriotism means meaningfully. So then we go to the row that actually tests whether the groups differ on patriotism after adjusting for the covariate. So that's our voting status row in this table. Can we reject the null that voter groups are similar on patriotism after we've adjusted for civic obligation? And if sig's less than 0.025, we'll reject that null. If it's greater than 0.025, we'll retain the null. And our sig here is 0.121. So that's greater than 0.025, so we're going to retain the null. What's that mean? It means there's no significant difference between voters and non-voters on patriotism after you take into account sense of civic obligation. So in the means you would want to use here are the means that are from the estimated marginal means table, the adjusted means that is. So our conclusion is that voters, with a mean of 119.98, did not significantly differ in the patriotism from non-voters at 111.56 after you adjust for their sense of civic obligation. We got to calculate partial eta squared, except SPSS gets it right again. So there's a formula, sum of squares of the IV in the numerator divided by sum of squares of the IV plus sum of squares of the DV in the denominator. And if you do that, you get 0.04. And note that is also what you get for the partial eta squared on the voting status last election line, 0.042. So there's our APA format. We've got an F with 1 in 57 degrees of freedom is equal to 2.48. P was greater than 0.025, not significant. And our eta squared, partial eta squared was 0.04. Again, remember to use the covariate adjusted patriotism means when you're interpreting this effect in your APA write-up. That's the 119 and 111 shown up above. So what does all this mean? Let's try to summarize what we got from the MANOVA and step-down analysis findings. First, we found that voters have a greater sense of civic obligation than non-voters, our primary DV. And then we found that after you take their sense of civic obligation into account, voters and non-voters do not differ in their level of patriotism. So back to the hypothesis, this does suggest that voters vote primarily because of their sense of civic obligation. That is, that's where the difference between voters and non-voters really is, rather than patriotism. And here's the means for patriotism. And you've got your unadjusted or crude and your adjusted means. There's a plot that goes into your APA write-up. The unadjusted means come from the descriptives table of the MANOVA, and that's also where you'll pick up your primary DV means, sense of civic obligation in this example, and that's what it looks like. And then on the right, we've got our adjusted means. Where do those come from? Well, those come from the estimated marginal means table on the MANOVA output, which is way at the end of the MANOVA output. And this is one where it gives you standard error instead of standard deviation. And if you need standard deviation, you've got to convert it. So finally, the step-down ANCOVA usually goes into a ANCOVA summary table in your APA write-up. You don't put all this stuff in the text. So you take that SPSS output from the ANCOVA, and you need those 3 rows, and you put them in APA format. Those 3 rows. Do note that bottom row for total, you have to hand calculate it for the sum of squares and degrees of freedom. You can't really use the total or corrected total rows. So that's MANOVA. Hopefully that makes sense. And now let's go do one.